Hello everyone, thanks for joining our tutorial. My name is Kai Wang. In this part, I will present works on bipeptide networks. Here is the outline of my presentation. So firstly, I will introduce basic notations of bipeptide networks. And then I will introduce the cohesive subgraph models on bipeptide networks, including core-like, truss-like, clique-like, and density connectivity-based models. Here we use G to denote a bipeptide network, or say a bipeptide graph, which consists of a vertex set denoted as V and an edge set denoted as E. Note that the vertex set can be further participated into two different vertex layers, which is denoted as U and L, and the edges can only exist between two different layer vertices. As shown in this table, we classify the cohesive subgraph models on bipeptide networks into 5 categories, and I will introduce each of the categories one by one. Firstly, I will introduce core-like models. The first model I would like to introduce is called the fractional key-core, which is originally designed to handle author paper networks. Generally speaking, it projects the bipeptide network into a weighted unipeptide network of authors, and which is a co-authorship network. And the weight between two authors can be computed using this function. Here, x and s prime denotes two authors, and y denotes the papers they have co-authored. So WE is the weight of the edge between these two authors. So according to this function, the weights between two authors are highly affected by the number of papers they have co-authored, and two authors have an edge if they have co-authored in at least one paper. And defining weights like this can ensure that the sum of all weights is the number of papers. Using such model, we can adapt the key-core decomposition algorithm for this weighted network to detect the hierarchy of the authors, and also we can find the dense regions if we apply the key-core algorithm. However, such projection method often suffers from two major drawbacks. Firstly, it will cause edge explosion, which means the number of edges of the projected graph can be much larger than that of the original graph. Also, it can cause ambiguous because of the information loss of one entire vertex layer. To avoid such graph projection, the generalized two-mode core is proposed on bipeptide graph by directly extending the key-core model. A generalized two-mode core is a subset of nodes C, which is denoted as core PQFG. Here, PQ are two integers and are two thresholds, and here Fg are two functions defined on the vertices. And we require that for all the upper layer vertices in C, Fu larger than or equal to P. And we also require all the vertices in the lower layer of C, GV larger than or equal to Q. And also we require the maximumability. Here are some examples of the functions. So basically, we can use the degree of a node within C. And also, we can use the input degree, the output degree, or in a directed network, we can use the sum of weights of links. Specifically, by using the degree function, the alpha-beta core model is further investigated. So the alpha-beta core is the maximal subgraph in which each upper or lower layer vertex has at least alpha or beta neighbors in the subgraph. And here is an example of the 1-3 core. This is because for each upper layer vertex, they have at least one neighbor, and for the lower layer vertices, they have at least three neighbors. The intuition behind the alpha-beta core model is that, comparing with the traditional K-core model, the vertex degree on two different vertex layers can be much different. So we need to use different thresholds for different layers. To efficiently retrieve the alpha-beta cores, in the literature, an index called the bicore index is proposed, which can support optimal retrieval of the vertices of any alpha-beta core, and the space complexity is only OM. This index is actually designed based on the nested structure of the alpha-beta core, which means that for a alpha-beta core, it is always a subgraph of the alpha beta minus 1 core, and it is always a subgraph of the alpha minus 1 beta core. According to such property, we can organize the alpha beta cores in a hierarchical way. Here we give an example of how to query the alpha beta core based on the bicore index. Suppose we want to retrieve the 1,3 core. Firstly, we go to the index IU and find the node block 1,3 and 1,5 and return the vertices U5, U1, U2, U3, U4, and U6. And then we need to go to the index IV to find the node block pointed by 3, 1. And then we will find three lower layer vertices V5, V3, and V4. Based on the alpha-beta core model, the alpha-beta community model is further defined by requiring the connectivity. Because the original alpha-beta core definition does not require connectivity, so which will group two disconnected groups into one alpha-beta core. By further requiring the connectivity, we can solve this issue and can use the alpha-beta core model to do community search. However, the alpha-beta core and the alpha-beta community model only ensure the structure cohesiveness, while overlook the edge weight in forming the community, which is also a very important factor. For example, in this user-moving network, each edge has a weight denoting the rating of a user to a moving. So if we apply the alpha-beta community model to search a community of hierarchy, we'll find this subgraph. And we can see it will include the movie Alien, which is not liked by Andy and Ken. And also, it will include the user Taylor, which has low ratings to 3 movies in this category, which means that she may not interest in such genre of movies. So the significant alpha-beta community model is proposed by further considering the edge weight on bipolar graphs. So we have defined the bipolar graph weight as the minimum edge weight in a graph G. And the significant alpha-beta community model requires the connectivity and the cohesiveness and also the maximality, which means it has the maximal weight among all the alpha-beta cores. For example, in the right example, we can see the subgraph in blue color is the significant 3-2 community, which excludes Alien and Taylor. By applying the significant alpha-beta community model on real-world graphs, we can see here is a user-moving network. The result returned by alpha-beta core model contains several low-rating edges, but the significant alpha-beta community model contains a more cohesive group, which means that if we use search result to do personalized recommendation, we have higher probability to find the community of the query user. Here we introduce another call-like model called strengthened alphabet call. The motivation is that alphabet call assumes the equal importance of edges, so it will blindly include both loosely connected regions and dense regions. And the state-of-the-art method to model tie strings is to use the butterfly support number. So a butterfly is a 2 times 2 biclics on biptagraphs, and the butterfly support number is the number of butterflies containing an edge. By using such concepts, we can define the strong tie as given a strength level tau. An edge is a strong tie if it is contained in at least tau butterflies. And also, we can define the vertex engagement as the number of strong ties of a vertex. So the tau-strengthened alphabet call can be defined by replacing the degree of the vertex as the engagement of a vertex. For example, in the right figure, the whole graph is a 2-2 call. By using the tau-strengthened model, we can exclude the relative sparse region containing 3 vertices U0, V0, and V1. In the next pages, I will introduce truss-like models. The truss-like model is usually defined based on the butterfly structure, which, as I told before, is a 2 times 2 biclic. So K by truss is the cohesive subgraph where each edge is contained in at least K number of butterflies. And consequently, the bi-truss number of an edge E is defined as the largest K such that a K by truss contains E. So in the literature, many researchers focus on the bi-truss decomposition problem, which is to compute the bi-truss number for each edge in G. For example, in this example, the edge U0, V0 has a bi-truss number of 2. This is because they can be contained in a subgraph where each edge has a bi-truss number of 2. Different from the K-by-truss model, the K-tip is proposed by imposing the butterfly constraint on each vertex. It requires each vertex is contained in at least K butterflies. In addition, the butterfly connectivity is required, where each vertex pair is connected by a series of butterflies. And also, the K-tip number of a vertex is the largest T such that there exists a T-tip containing a vertex. So tip decomposition also aims to find the tip number of all the vertices. And the main idea of tip decomposition is similar as the peeling algorithm of K-call or K-truss. Firstly, it counting how many butterflies each vertex participates in, and then it iteratively assigns tip number in a non-decreasing order. For example, this subgraph is a 2-tip. Another truss-like model called quasi-truss is defined on biped graphs based on the concept of special edge. If two vertices from the same layer share some common neighbors, then a special edge is added into the biped graph. For example, in this figure, because H and I share common neighbors V1, V2, and V3, so there is a special edge denoted as dotted line is added into the biped graph. So with more triangles sharing a unique special edge, a dense subgraph in G is expected to be identified. After that, we can identify the maximum quasi-truss, in which is the subgraph in which a special edge is contained in the maximal number of triangles. So after obtaining the quasi-truss, we can remove these special edges, which result in dense subgraphs in the original bipolar graphs. Next, I will introduce the clique-like models. On bipolar graph, the biclique is a complete bipolar graph, and a biclique is called a maximal biclique if it is not contained by any other bicliques. Beyond this, we also have the definition of maximum edge, maximum vertex, and maximum balanced biclique. For example, in this figure, this subgraph is the maximum edge biclique because it contains the maximum number of vertices. It is also the maximum balanced biclique because it contains the maximum number of equal vertices in two different vertex layers. And also, this biclique is the maximum vertex biclique because it contains the maximum number of vertices. So in the literature, the maximal biclique enumeration problem is well studied. It aims to find all the maximal bicliques. Note that the outputs of maximal biclique enumeration will give us the result of maximum edge, maximum vertex, and maximum balanced biclique, and it is a NP-hard problem. If we want to directly find the maximum vertex biclique, it is not a NP-hard problem. It can be solved in polynomial time. And if we want to find the maximum edge or the maximum balance biclique, they are both NP-hard. But we can design further pruning rules to accelerate the computation process. To enumerate all the maximal bicliques, the branch and bound framework is usually used. So we maintain a partial biclique and recursively add vertices into it and check maximality. So, for example, in this figure, from the root node, we can directly add vertices to the partial biclique, and if there is a non-maximal biclique, we just stop the iteration. Besides the definition of biclique, we also have quasi-biclique. A quasi-biclique is almost a biclique in the sense that we are allowing it to miss a certain number of edges. For example, here is the example of gamma quasi-biclique, which is defined based on the connectivity and density. And we also have the epsilon quasi-biclique. So the epsilon quasi-biclique is defined based on the degree. We can see the definition. The vertex set is epsilon close to being a biclique if every vertex in the vertex set is adjacent to at least 1 minus epsilon portions of the vertex set in the opposite layer. So we also have other models including the alpha quasi-biclique, the error-tolerant epsilon quasi-biclique. Next, I will introduce the density and connectivity-based models. There are several metrics to define the bipolar graph density. For example, for given a bipolar graph G, for any induced subgraph ST, we can define the density like this. We can use the number of edge divided by the square root of the number of the vertices. So this example, if we compute using such metric, can compute this density. So another way to define density is using the number of edges divided by the number of vertices. So if we compute the density using this metric, we will have a different result. Another way to define density is based on the concept of PQ biclique. Given a bipolar graph G and two integers P and Q, its PQ biclique density is defined as the CPQG divided by the number of vertices, where CPQG is the number of PQ bicliques in the G, and a PQ biclique is a bicyclic consists of exactly p upper vertices and q lower vertices. So we also have the concept of PQ bicyclic density subgraph, which is the subgraph has the highest PQ bicyclic density among all the possible subgraphs. For example, in this figure, if P and Q are set to 2, then the two-chip bicyclic density in the network is this subgraph. The difference between the PQ bicyclic density and previous density metric is that it can be adjusted by adjusting the parameter P and Q. Consider the connectivity. We have the definition of k-neighbor graph. Given a bubble graph G, the k-neighbor graph GK is defined on the upper layer, which can also be defined on lower layer. So if two vertices has an edge, if they share at least k neighbors in the original graph G. For example, below is the two neighbor graph and three neighbor graphs of G. We can see U1 and U2 has edges in the two neighbor graph, but does not has edges in the three neighbor graph, which means that they has two common neighbors in the original graph. So this concept is also based on the graph projection, similar as the fractional k-call. Now is the conclusion of this part. We have introduced different groups of cohesive subgraph models. The cohesiveness constraints are formulated differently for this group of models. For example, they can use degree, use butterfly to formulate different cohesive constraints. And also, in the first three groups, most of the model have the nested property. And like the unified network cases, there exists a trade-off between the computational cost and structure cohesiveness for these models. For example, the core-like model are usually can be simply computed, and the clique-like models are usually hard to compute. That's all for my presentation. Thank you for listening. You can ask me if you have any questions.